Hello everyone. Today we'll be learning about scalars and vectors, what they are, and a little bit of how to use them. Here we have a picture of a vector coming out of the origin in a coordinate system. Now scalars are something that you've been using for a very long time now, probably all your life, but you've probably never thought of them as scalars. Scalars are just any quantity that can be completely described by their magnitude, or their bigness or size. And so some examples of scalars are distance, which is measured here in this odometer, temperature, speed on the speedometer, volume, and just ordinary numbers. All of these scalars can be described completely by how big they are. They don't point in any particular direction or anything like that. But the reason that I bring this up is because vectors do. Vectors have both a direction and a magnitude. We can see that this windsock here is measuring the wind speed as a vector because it tells us both the size of the speed of the wind and the direction that the wind is blowing in. So some examples of vectors are displacement, velocity, acceleration, force, and momentum. And we'll be covering all of these a little bit later on. Now, vectors need both a magnitude and a direction to be completely described. So there's no use in saying 10 newtons of force. You have to say 10 newtons of force downwards, or something like that. Now, when we draw vectors in diagrams, we represent them by arrows. So we can see some arrows over here. Now, the length of the arrow shows the magnitude of the vector. So, longer arrows mean bigger vectors. We can see that the arrow at the top is larger than any of the other vectors on this diagram. The direction of the arrowhead, it shows the direction of the vector, so that's pretty intuitive. These top vectors are pointing to the right, and these bottom vectors are pointing in opposite directions. Obviously, vectors can have any size in any direction, just like scalars can be as small or as big as you would like. Now, vectors can be written in a number of different ways when we're writing them algebraically. We can write them with a little arrow over the top, which is what we'll be using in this presentation. Sometimes when they're printed, the typist will use boldface to represent vectors. And if we're handwriting them, we can write a little squiggle under the vector to show that it's not just a scalar. Multiplying a vector by a scalar changes the magnitude of the vector. So we can see in this diagram here, we have one vector called A, and 2 times A produces a vector which is twice as long and points in the same direction as A. If we multiply a vector by a negative scalar, like -1, then it reverses the direction of the vector. So we can see that we've got the same scalar, so the same vector, A, multiplied by -1, and produces another vector with the same length as A, but in the opposite direction. Now vectors can be added together by joining them from head to tail. So we can see vector A and vector B, if we add them together, joining A's head to B's tail produces this little triangle, and this green vector is the sum of the vectors, A plus B. We can see that adding 2 vectors together can produce a vector pointing in a different direction to either of the 2 original ones. So A was pointing sort of up and to the left, B was pointing sort of down and to the right, whereas A plus B is pointing down to the left, which is a different direction to both of the starting vectors. A vector can be subtracted by first reversing its direction, so making it minus b rather than plus b, and then adding it head to tail to the other vector. So we can see that when we reverse b's direction and then add that to a, we end up with this vector over here, a minus b. We'll be working on vectors in a little more detail later on. So that's the end of the theory. We've covered the definition of scalars and vectors and a few of the things you can do with them. Let's go on to some questions. Which of the following is a vector? Well, let's go through the options. 1 degree Celsius. Degrees Celsius measures temperature, and temperature doesn't point in any direction. A temperature can be defined completely by how big or by how small it is. And so this must be a scalar. How about B, 2 meters squared? Well, meters squared measures area, and area doesn't really point in any particular direction either. And so, this has got to be a scalar. Well, how about D, 4 kilograms, or 4 kilograms in mass? That doesn't really point in any direction. A mass of 4 kilograms can be pulled downward, but it's not a property of the mass that the object has. And so 3 newtons downward is the last answer. Newtons measure force, which is always directed. And saying 3 newtons downward almost gives it away, because we have a direction where none of the other scalars needed a direction to be defined completely. So this is the correct answer. Question 8. Which of the following is not a vector? That is, which one is a scalar? Well, let's take a look at the options. A, 10 miles per hour west. Now, if the quantity had just a magnitude of 10 miles an hour, then it would just be a number, a scalar. But because we're saying 10 miles per hour west, we have direction, and that turns it into a vector. And so this is a vector and not a scalar. Or B, 4 light years towards Alpha Centauri. Well, the quantity has a magnitude, 4.4 light years, and it has a direction towards this star. And so this has to be a vector as well. How about 3 volts per meter toward the negative plate? This is a measure of electric field, which you won't be touching on for a while yet. And so you've probably never heard of volts per meter. But we can see that there's both a magnitude, 3, and a direction toward the negative plate. So we know that this must be a vector as well. Our last option is D, 7 moles of oxygen. Now, this is more of a chemistry measurement, but we can still define it as a scalar or a vector. We can see that the 7 moles of oxygen isn't pointing in any particular direction. There's only a number defining how big it is. And so we find that this must be the scalar. Because it has no direction, it can't be a vector. Question 9. Add these 2 vectors together. What is the magnitude of the resultant vector? Well, remember to add 2 vectors together, we join the first vector's head to the other's tail. And so, drawing them again, it looks something like this. And the resultant vector, of course, moves from this bottom point here to the end point, and looks something like this. And this produces, of course, a right-angled triangle, because A was going all the way to the right and B was going all the way up. And so, in a right-angled triangle, we can find the length of the hypotenuse by using Pythagoras' theorem, a squared plus b squared equals c squared. Substituting the lengths of the vectors, we replace a squared with 4 squared and b squared with 3 squared. And we see that equals 25. And so because Pythagoras' theorem says a squared plus b squared is c squared, we see that c squared must be 25. And so that's the magnitude squared of this vector. And we find that the length of the vector c is 5. But this doesn't completely describe the vector, remember. It tells you its magnitude but not its direction. Its direction is up and to the right. Question 10. A vector A and has a second vector B added to it. The resultant vector points in exactly the same direction as A pointed. So what can we say about B? So I'll just draw this quickly. We have A over here. And we have A plus B, which is moving in exactly the same direction. Now the only way that this can happen, if we add 2 vectors together, is if B is pointing in the very same direction as A. And so that's one of the things that we can say about B. But there's also another way that this can happen. If A starts off long, like so, and then becomes very short when B is added to it, like this, then it's still pointing in exactly the same direction. And so in this case, B must be pointing in the opposite direction. But it has to be less than the length of A, otherwise the resultant vector would be pointing in the opposite direction as well. So we see the answer is either B points in the same direction as A, or B points in the opposite direction to A and has a smaller magnitude than A. It's important when adding vectors together to remember their direction. Adding a very negative vector to a very positive vector could change the direction of the resultant vector. So this concludes the questions. Today we've learned about what scalars are and what vectors are, how to work with multiplying scalars to vectors, and how to add vectors together, which we'll cover more later on.